Okay, I've just started a GPU on RunPod, and you have to wait a few minutes before it will allow you to start JupyterLab. So I started the A40 GPU, and I started JupyterLab. So I'm just going to upload my case. So I'm going to select from my work directory, if I can find it, the octree solver. The latest compiled version of the GPU is that one. So I just need the executable, the input file, and the geometry. That's all I need in order to run a case. I'm just going to run this case at a higher speed just to see how it compares. So they've uploaded, so all I need to do is to make that executable. Once that's executable, I can run it. Like that. So that is the UFOCFD octree solver has just started running. So it's read in the input file, and then it just verifies all of the input variables that I've specified beforehand. So it's read in the STL file. It started to make the octree. It does the base refinement, which is the refinement of the STL. Then it does the background refinement up to whatever level you specified. Then it does the neighbor refinement to make sure that all cells have neighbor cells are refined. And then it does the blanket refine iteration. So depending on how many blanket layers you specify. So I've specified 2. The mesh size would go up rapidly if you specified 4 or 8, for example. So I've just specified 2. So this is then creating the point octree. So it uses a separate octree for the points. So there's one octree for the STL file, and then there's another octree for the points. That's just the way it's written, so it's a little bit confusing. Then it's about to start running, so it just confirms the mesh sizes. So the octree is 58 million. The leaf cells 51 million. The number of points 54. The number of octree points 112. So that is refined down to 0.24 meters. So the actual live cells that we've got is only 20 million, so not that much considering the overall mesh size. So we're solving on 20 million live cells, and this is outputting every 10 iterations, so it's done 400 iterations already. So yeah, let's just go back to the input file. Got the geometry, specify that it's binary, set up the VTK slices. The maximum level is 11, so we've got the basic octree. The root cell is one massive single cube, and then we've got 11 levels of refinement. So the background levels is only 4. The background mesh, 2 blanket layers, and then I've opted here to select limits on the STL size and the octree cells, the point limit and the point octree. So yeah, this specifies the location of the root cell. Number of iterations, 20,000. I should have set that to 10, but I'll come back to that in a bit. The write frequency. Smoothing is either 2D or 3D smoothing. You can have local or global time stepping. You can have subsonic or supersonic or stagnation conditions. So at the moment I've got viscosity and turbulence off, so it's just an inviscid flow solution, but those options are coded. Smaggerinsky's, that's if you're using turbulence. That's a turbulence limiter. All the stuff at the bottom is just additional refinement, so we can forget about that. This is for the smoothing, so you can specify pressure or density based smoothing. CFO number, min and max smoothing, you don't vary those. The main thing that you vary is the wiggle cutoff, which sounds a bit odd, but that is just the size of the wiggles in the flow solution. So if you want more smoothing, you have to reduce that number to sort of match whatever is the maximum wiggle size in the flow solution. There's a wall function value. So you can leave that at 1, but I found for this particular solution, there's certain areas where the geometry is very thin and it can cause spurious problems in the flow solution, but I found that just reducing that to 0.98 is enough to deal with that. Normally it's not a problem, but on this particular case it has been a problem. So I'm running at 200 here, so previously I've been running at 100. So these are all in the flow conditions. So this is a compressible flow solver, so for it to work properly you need to have quite a high velocity. So this case that I'm looking at is the Niigata test case from the AIJ website. So it's a pedestrian wind comfort case. So you can do your validation at various different wind directions. I've just been validating against this one case, which happens to be the westerly wind direction, just purely because it's from left to right. So if I wanted to look at any other cases, I'd have to rotate the geometry a bit and then rerun it. So that's why I've just been running this one test case initially in the westerly direction. Switch the perspective off. So the domain size for this is, when I've been solving it in the lattice Boltzmann solver, I've been doing 600 by 500 by 60, which is a uniform mesh in lattice Boltzmann. So if we look at 600 times 500 times 60, 60 is the building height, so you don't really want to go below that. So even if you have 1 meter cells, that domain size is going to give you 18 million cells mesh. So you can see that ramps up very quickly. So if you have half meter cells, multiply that by 8. So half meter cells everywhere over that domain size, and you end up with 144 million. And I have run several cases of lattice Boltzmann solver like that one. If you want to go to quarter meter cells times by 8 again, and you've got a mesh size of 1.152 billion, which is doable. I can run that on on RunPod GPUs, but it could take 12 hours to run. I generally run things for, well, the lattice Boltzmann solver, I'd run it for 100,000 iterations, so that you can see the development of the flow solution and all the unsteadiness. So that's quite a big case, and then that's going to cost you $4 an hour or whatever it is. So that's why I've come to start using this octree solver, so I can get quicker flow solutions. So with the octree solver, you can have quarter meter cells around the geometry, but the cost is only going to take sort of whatever it was 50 million cells, and you're only solving on 20 million, so it's a lot more manageable and it runs a lot quicker, and it's a steady state flow solution, so you're looking for a converged flow solution instead, so it's a lot quicker. This also says directory not found, but so that's going to keep running now until it's finished. So I'm going to cut off this and then come back to it a bit later. Okay, so I'm just going to come back to this case now while it's still running. It's nearly finished. If we go to the pod, you can see that it's running at 30% of the memory. So if I click on this and go to telemetry, you can also see that on the A40, its utilization is 100%. On the RAM, it's 32%. So we're only using a third of the available RAM. Literally just finished running. It's written the output files, and that's that done. So I'm just going to copy the output files. There's just 2 of them on the convergence. So I'm going to download them. So that takes a few seconds to download. This is just a slice in the X and Y direction. So I'm going to copy them into my working directory, which I've lost. Octree, and I've got a post-processing directory. So I'm going to copy those results into there. Get rid of those files. So BTK files. Right, what I want to do now is to load the state so I can actually have a look at the results. So I use a state file because it's got everything saved as it's like I want it to be. So it takes a few seconds to do that. Right, because I've run this one at a higher speed, I need to normalize it by a higher speed. Like so. So this is just showing me the probe data on the left here, because the solution's been resampled onto these test data points, and then I plot the output and then I save that. So I'm going to save that as a CSV file. And then the CSV file is here. I just need to remove the commas from that. Remove the commas. I can have a look at the convergence. Just need to load the X window. Let's try that again. So this is the convergence. Actually, the maximum velocity should be flat. That's quite wiggly, so that isn't properly converged. The wiggle is around 0.1, so that's okay. That's what I've set. But we'll have a look at the solution anyway, just to see where we're at. So I can now look at the solution just by doing that. So this is comparison of CFD with experiment. CFD is purple, So compared with the test data, it is capturing relatively well these peaks, and the magnitude of the peaks is pretty good. These 4 big peaks, they're the high velocity regions, so it's captured those quite well. Remember that even though we're running this at 200 meters a second, we're normalizing it by the free stream velocity. So that's what these values are. But then it's not capturing quite so well the velocities, the low velocity regions on some of the narrower streets. So then I can run the Pearson correlation. Pearson correlation is 0.76. Well, that's not brilliant, but it is what it is. So I've managed to get a value of 0.8 when running it at a constant velocity of a lower speed. So yeah, let's just have a quick look at this as well. Get rid of that. Get rid of the plot data. Get rid of the resample with dataset. So you can see these are the probe points. If you can see those there, are these tiny white dots. And the flow solution here is going up to 330. So if I put the geometry on, you can see that. Put it into 3D mode. Get rid of the perspective. So that's what the flow solution looks like at a particular slice. A slice at 2 meters. So if I put on the surface with edges, you can get an idea for the mesh refinement. So if I zoom in a bit to some buildings, we've got 1/4 meter cells around the edges of the buildings, and then larger cells elsewhere. So I should also be able to load in the other J-slice and view that in the same way. So I can put the mesh on that. I can change it to velocity, take the mesh off. So that's what a flow solution looks like. It's not the best flow solution that I've obtained, but this was obtained, or it can be obtained within 15 minutes of running it on the A40 GPU.